want to go back over anything that you're having questions on, because we've got today, and then next time we have a lab and a review Kahoot, and then the test. So I want to make sure that you're all up on board. Yes. Any of the assignments.
Okay, so on this parts per million one, I didn't understand question 6. Like, I don't know how to do that.
Okay, so parts per million, if we go back, let me go grab the question was on the stuff you did last time, on the parts per million. I'm going to grab one of each of these so I can project it. Whoops, I grabbed one. Okay. On the very front page of that packet that you were given, it sort of goes into right here what you need to get parts per million. So you either need to be in milligrams per milliliter or milligrams per kilogram. Okay, so whatever you're given, and on number 6, you're given here milliliters and liters. So on this one, we want to be in, what did it say? Milligrams per liter. If I have water, it's a 1-to-1. So I can assume, because they haven't told me what it is, I'm going to assume that I have a gram. This is not a real great question. I will tell you that right off. It should have said milligrams. So basically take this as being milligrams, and all you have to do is take and divide the two. On the back part. Yeah, these should have been milligrams on both of those because they haven't given you what, and I didn't do this, so just bear with. These should all be milligrams. So then it should be fairly easy. You just need to be milligrams per liter. So you're dividing milligrams per liter, and that gives you parts per million. Easier? You okay? We okay? Make it easy? All right. Okay, sorry about that. I didn't double check that. We will change that for next year in the group. Okay, anything else? Anybody else have any questions whatsoever? Yes, ma'am.
On this week's worksheet, I don't know how to do the back.
Okay, the back is just reading from the graph. So you've got 3 graphs up at the top, A, B, C, and D. Okay, I don't have a copy of that one. Yeah, here, I'll just take a picture real quick. Okay, so this is the one we're talking about right now. So I'm going to just zoom out just a little bit. Focus, take a picture. Okay, so on this one, all you have to do is basically read from the graph. So when you get down to this part, that just means melting point, boiling point, sublimation point. If you have a melting and a boiling point, you don't have a sublimation point. So it says, at 1 atmosphere, go across. So I'm going to grab a colored pen to go across at 1 atmosphere. So on this one, if I go across at 1 atmosphere, I'm a little below, I'm going to have a melting point, and I'm going to have a boiling point, because that's what that is. So I'm just going to write those numbers down there. Remember, the answers are at the bottom, so you can cross them out. Okay? So if I have a melting and a boiling point, I'm not going to have a sublimation point, because the sublimation point is below that point. And if I have a sublimation point, that's this line right here, I'm not going to have a melting and boiling point because I'm too low. Okay, so right here on this one, I can put Na right there because sublimation point's not applicable. And this one, I'm just going to come straight down and say, okay, it should be about there, it should be about there, and I'm reading down at the bottom to find which ones are close to that. Okay, so remember our graph stories? We've been sort of pounding you with graph stories. Graphs tell a story, and you've got to be able to read off of them. These tell stories. You've got to be able to read off of them. And these are the questions we have about this story. Does that help? Did you have any other questions on that? Good. All right, anything else? Yes, Todd?
On the polarity method, back.
Mm-hmm. To volume to what? Are you calculating?
Volume.
Oh, you're trying to find volume in liters. Okay, he's asking about the molarity thing. Remember, molarity is moles divided by liters, right? And if I'm trying to find liters, here it is on the bottom. So basically what happens is these two trade places. So liters becomes moles divided by molarity. Okay, so it's just solving for one or the other. If I was trying to solve for moles, it would be molarity times liters. I'm just rearranging the equation. Okay? Yes. Read it out loud for me, Todd. Okay, go slower. 2 point. Whoa. Okay, how much? 200 milliliters. Okay, molarity. So I've got everything I need. All I've got to do is change this from milliliters to liters. So divide it by 1,000. So what do I get? 0.2, good, liters. And then I'm going to use the mole one because I know from moles I can get 2 grams, right? So I'm going to take moles are equal to the molarity times liters. So 2.5 molar times 0.20 liters. That's going to give me moles. Okay, and how I knew that is potassium is a +1, carbonate is a -2. This is a review, too, of how to write formulas. That's why we gave it to you in words, because you have to know how to write formulas. All right, so somebody plug that through for me. What do we get? 0.05, and okay, moles. So now what I'm going to do is, I'm going to extend this up so we have more time, more room, is I'm going to take that potassium and look it up on the periodic table. I don't have this one memorized. I think it's 30-something. 0.098? Okay, great. And then I have carbon, and we should all have that one memorized by now, right? And oxygen, and we should all have that one memorized by now. Seems like we use it over and over and over and over again. And we add those up. So all I'm doing right now is finding the mass. Okay, if you haven't turned this worksheet in, you should be doing this problem with me. What number is it? 1. Number 1. You should be doing number 1 with me because, dang, you get points for just writing it down. Okay? What do we get? Anybody got that added up? So number 1 on your molarity worksheet. I think it's molarity 2, isn't it? Molarity 2 worksheet. Okay, good job. That's how many grams there are in 1 mole, right? Well, then all I have to do is take 0.05 moles of K2CO3, and I'm writing it underneath because I'm not going to have very much room. And I know now there's 138.204 grams of K2CO3 in 1 mole of K2CO3. Moles of K2CO3 go out, and I just take those two and times them together. It looks like I only had one significant figure. Was it 200.0 milliliters, or was it just 200? 200.0, so I actually have 2 significant figures, because that was 0.0, that had 4, and this one had 2, so I report 2. So somewhere around 6.9. 6.9 grams of K2CO3. Is that more helpful? Okay, what else can I do to help you with what you've got out there already? Huh? Well, we got to go on to the last little thing today, and you're going to have a little assignment with it. So, yes, ma'am. Oh, are we off here? Are we off? Double check that. I got 2.5 times 0.2. Just 0.2. Okay, so we're off. This should be good catch. So this should be, does that affect that? Now it's 69. Okay. Great check. Make sure you say something, because I'm relying on you guys for calculations. That's a great check. Okay, anything else? Any others you want to go over? Okay, what we're planning on doing today is I'm going to go through colligative properties with you. We're going to do the pre-lab for next time, and then we'll do a little exit quiz on what we're learning today in class. Okay? All right, so grab your notes out because we're going to finish those up today. It didn't slide it over far enough. I can't grab it. There we go. We're on to solutions. Okay, just a quick review as we go through solutions. What dissolves in what? What's it called? Something dissolves in something else. What is that called? Solute. What is it dissolving in? Solvent. And it makes a solution. Good. Okay. So we're going forward here. This is a fancy word. Factors that affect salvation. No, it's not like praise the Lord kind of salvation. Okay. It is how well it dissolves. Okay. That's what salvation means. Okay. So we already know, if you've ever made Kool-Aid or you made frozen juice drinks or anything like that, you know that you got to agitate it. You got to stir it, right? The surface area, if I try and make Kool-Aid with sugar cubes, it's going to take a lot longer than if I just make it with powdered sugar. Okay. If I heat the water up before I try and dissolve the sugar, it's going to go dissolve a lot faster, even though I really don't like warm Kool-Aid, but I can cool it down after. So temperature affects it. So three things that really affect it. Something dissolving in something else. Okay, that's important. So you have these in your notes. Agitation is not something that, it's a big word for what? Stirring. So give yourself a way to remember that. It's a way of first stirring. Okay. And what is surface area? By what I just described. Powder. So this is sort of harder to describe, right? Surface area. It's how much area that I have exposed, right? So it's how much area do I have exposed. So if I had a sugar cube, the outside area is not very much, but if I powder that sucker, then each of those little grains is now exposed. So it's the amount of area that I have exposed. And then temperature, we just need to know that as I increase temperature, for the most part, I'm going to put a little caveat there, for the most part, things become more soluble. Now, there's always that ornery kid that doesn't want to do what everybody else does, and they want to do their own thing, right? So sometimes we've talked about exo and endothermic processes, right? If I have an endothermic process, I'm putting heat in to make the reaction go. So if I put more heat in, it goes faster. Well, if I have an exothermic process, which means it gives off heat, if I put heat in, it says, oh, yuck, I'm going back to my products or my reactants. So it's opposite, okay? So temperature, for the most part, increases solvation, but you've got those exothermic processes that it actually slows down. Okay, so then we got to talk about solubility. We have saturated, unsaturated, and supersaturated. I found this couple pictures that sort of help me to visualize what's going on here. So unsaturated, I can put more stuff in. It's sort of like when you make Kool-Aid normally, you can put more sugar in, like my kids did. And you can put more sugar in until finally it becomes a saturated solution. No more sugar will dissolve at that temperature. Okay, hint, what did I just say? No more sugar would dissolve at a specific temperature. So that's saturated. To get to supersaturated, this is how you make candy, how you make divinity, how you make all these hard candies. You take sugar and water and it looks like it's never going to dissolve, and you heat the sucker up. And then it dissolves and you get this syrupy mixture. And you got to be careful how you cool it down, because if you cool it down too fast, you get crystals and then it's not so nice. It's sort of yucky. Okay, but if you cool it down slowly, it stays in solution, and that is a supersaturated solution. Okay, I'm hoping this will work. I've got a little video here. I'm hoping it comes up. Let's see if it does. It's thinking about it. Oh, darn. Let's go back. I have to just grab it and bring it up. Oh, it brought it up on the other screen. How nice of it. So they've made a supersaturated solution, and you can do this by taking about a liter of vinegar and about a teaspoon of baking soda and adding it really slowly, and then heating it up, and then cooling it down. It's supersaturated, so any little particle will set off the crystallization. Pretty cool, huh? And now watch what he's going to do after this, because you can actually pour a tower. They call this hot ice because it looks like ice. Or it could be a she, I don't know. The fingers to me look like ice. Just keep growing. You can do this at home. So baking soda, about a teaspoon, and about a liter of vinegar, and you just put it on the stove after, baking soda and vinegar will do a reaction, so you got a pretty big container. And then you just heat it up until it gets sort of a skin on the top. Put it in a clean container. It's got to be really clean, and let it cool down by itself. Once it cools down, then you can take and do this. It's pretty fun. Yeah. Have you ever had the reusable hot hand things that they have a little clicker in the center? This is the same stuff. So anyway, I thought that was pretty cool. It's really tricky to get it just perfect, so it might take a few times doing it to get it to do, but I think that's just awesome. It just keeps growing. It's like a stalagmite thing going on. It's hot. Yeah, it's hot. Crash. And now he's going to go do it again. He's just putting it all out. Now he's got it in a clean container. The other one he had a seed crystal in. Now he's just taking a piece and he's going to put it in and see what happens. It's so fun. Science can be awesome. Science rules, that's right. Okay, so let's go on here. So this is a supersaturated solution. I would never do this in a big flask, but you can, and then you have to heat it up to re-solidify or re-get it into solution. It's sort of a pain. I've broken a couple flasks doing that, so you got to be careful. Okay, so colligative properties. Colligative properties is adding a solute to a solvent. So we've already defined what those two are. And what happens to the properties of the solvent, they're modified. Things change. They act differently in the solution. Vapor pressure decreases. What's vapor pressure? Pressure of the gas above the water, okay? We'll go into that a little bit more. I'm just going to list them here on this slide, and then we're going to go into each one a little bit more. Melting point decreases. Boiling point increases. So they call it melting point depression and boiling point elevation. Okay? And then osmosis is possible. You get osmotic pressure. And that's important because that's how our kidneys work. Okay? These changes right here, these four changes are what we call colligative properties. So these are all encompassing of colligative properties. They depend on the number of solute particles relative to the solvent particles, not the kind of solute particles, and that's going to be important. So I'm going to pause this, let you write this down, and then we'll move on. Okay, so let's go on and talk about each one of these. So the first one, vapor pressure lowering. We worked with phase diagram. It's basically when I have when I add a solute to a solvent, it takes its phase diagram and it lowers its melting and boiling point. Okay, so when I add a solute to a solvent, it lowers the melting and boiling point. And because it lowers the boiling point, it lowers the vapor pressure, which is when I'm boiling. I get the pressure of the vapor. Boiling point actually increases. But the vapor pressure lowers because we get a lower time it's at. Sorry, I'm reading that wrong. The whole graph, though, goes down, is what I was trying to say. So you mean if it was flat like this coming out? It would come down and it'd be like this. It'd actually come down, okay? So my boiling point, because by the time when I come out to here, well, let's do it this way. It still would be the same distance. I would just be lowering it. So this distance here to here, we actually get a higher boiling point in a solution. So when I'm making, like, when you make macaroni and cheese, okay, they tell you to put salt in the water because they want the temperature of the water to be higher. Now, if you've ever done any backpacking, you want to put a lot of salt in the water and then rinse it off after because you've got to get the boiling point up to where it normally would be. Because if you're high in the mountains, the boiling point's lower and you end up with mushy noodles. They never do get cooked if you don't put enough salt in. And if you don't rinse them out afterwards, then you have this nasty salty noodle effect. So if you've ever done any backpacking, that's the first mistake of first-time backpackers is they try and boil noodles up in the mountain and they end up with mush, which isn't very appetizing. Okay, osmotic pressure. This is when, like if you stay in your bath too long or stay in the swimming pool too long, you get granny hands. That's because you've experienced osmotic pressure. Okay, you have more salt than the water around you, and so you're trying to dilute the water around you. So stuff is coming from you and going into the solution or the water around you to try and make it, anyway. So it always moves from low solute to high solute through a semi-permeable membrane. That's how kidneys work. So change in boiling point, we talked about that by adding the salt, macaroni and cheese. That's how I remember that. It also has to do with your car. That's why we put antifreeze in our car. It's not just so it won't freeze, it's so that in the summertime it won't boil over, hopefully. Okay, unless it gets way too hot. Okay, change in freezing point. We add ethylene glycol, which is antifreeze, to water, so that we'll lower the freezing point. So it just doesn't, my car doesn't freeze up at 0 degrees. Okay. We use this a lot of ways, from antifreeze to putting salt on the roads, which we've experienced here in Utah, right, with nasty weather, to making ice cream, homemade ice cream. Okay. Which would you use in the streets to put down, and would it depend on temperature that's outside to decide what I put down? These are the things I use to put down on the streets. So they've got sand, they've got rock salt, and they've got ice melt. So first of all, what's the cheapest? Sand, and then rock salt, and then probably ice melt. Ice melt's probably more expensive, right? So as a city manager, if there were ice out on the road, what else would determine which one you put down? What would be most effective? How do I know? Todd? The properties. SiO2, look at where that is on the periodic table. SiO2, where is it on the periodic table? Is that going to be an ionic, polar covalent, or covalent bond? It will be covalent. How do you say? How do you know? Oh, silicon and oxygen are close together on the periodic table, so it's going to be covalent. Covalent things don't like to split into ions. They like to hang together. They're sharing. So silicon oxide, sand, won't separate. Well, that makes sense. When I throw it down on the ground, it doesn't dissolve and go away, right? It just stays there. Okay, so it has what we call an I factor of 1 because it is just one particle. It won't separate. But what happens to salt when you throw salt down? It dissolves. What does it dissolve into? Dirt? No, 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 no. No, what does it dissolve into? Ions. What are the two ions it dissolves into? Na plus and Cl minus. Good. So I have 2. We have an I factor of 2 here. Ice melt. Look at where they are, calcium and chlorine on the periodic table. What type of bond? Ionic. So it's going to dissolve into ions. What ions is it going to dissolve into? Calcium and 2 chlorines. So it's going to have an I factor of 3. Okay? So as I look at this, sand I can use when it's not very cold. So it's right around freezing. I can throw that sand out and it will help melt the ice. It will lower the freezing point of the ice by a factor of 1. If it's a little bit colder outside, I want to put some salt down because salt will lower the freezing point by twice as much. If it's really, really cold down, even though it's more expensive, in my more problem areas, I would probably throw some ice melt down so I didn't have accidents, because that will lower it by a factor of 3 when it's really, really cold. Does that make sense? Okay, let's move on. This is the equation that we're going to be using for both freezing point depression and boiling point elevation. Okay, so you'll want to write this down. This is the thing that changes. It's either constant of boiling or constant of freezing. The I is what we call the Van Hoff factor. That's what I was just talking about. That's how many parts does it break into? How many pieces am I going to have? Okay? So for ionic compounds, we need to look at, say, and polar covalent compounds, we need to say, okay, how many ions will this break down into? And I got to remember my polyatomic ions hang together. So like PO4, phosphate, hangs together. It doesn't break down into phosphorus and oxygen. It still hangs together. Okay? So let's look at this. Here's a compound, glycol. Ooh, glycol, okay, it's 1. It's a organic. It's a covalently bound. That's what we put into our that's ethylene glycol is what we put as a antifreeze. NaCl, we just talked about that. How many? 2. Good. I'm going to move this because it's going to come up in the wrong place. CaCl2, 3. Okay, now I'm going to be tricky. Calcium phosphate. How many? I hear 2, I hear 1, 11. Think ions. How many ions is it going to break into? How many ions? This is a polar covalent, so anytime you have a polyatomic, you're going to be polar covalent, more on the ionic side. How'd you get 5? There's 3 calcium ions, 2 phosphate ions, good, total of 5. Do you see how he got it? Okay, oh, don't fall asleep on me, man. Stay with me. Okay, so we got 5, okay, calcium phosphate. All right, so you're right, if it comes up, 5. All right, so what we're going to be doing here is we're going to be working with KFs for freezing point, KBs for boiling point. The one that we're going to be worried about the most is water. So if you would write down the KF for water and the KB for water, those are the ones we're going to be using the most. Are they there already? They might be in the chart. You might want to highlight them. Now, the thing that we want to remember is freezing point was what? Freezing point, it lowers the freezing point, right? So I got to remember that this is going to be a negative. I'm going to take it away from the freezing point of water, which is 0, right? 32 Fahrenheit, but we don't use Fahrenheit, so it's 32 degrees Celsius. And boiling point, it elevates, it makes it higher. So I'm going to be adding whatever it is at the end of this one. So if you'll put a reminder that KF is going to be below the freezing point, and KB is going to be above the boiling point, that will help you. We're still going to use this equation. Now, this M right here should be that cursive M, the lowercase. Remember I italicized M? That's molality. Oh, wait a minute. We did a quiz on molarity. Molarity was moles per liter. Molality was, what's molality? Molality. Do you remember? Molality is fat, so what is it? Moles per kilograms. Kilograms. Okay, moles per kilograms because it's fat. Okay? All right, so let's try some of this. Say that I had 62.1 grams of glycol, which is 1 mole of glycol. I'm not even making you calculate moles. So we got 1 mole of glycol. Okay, in 250 grams of water. What is the boiling point? So what's the first thing I need to figure out? Grams to kilograms, good. So I'm going to need to get the grams to kilograms. I can look up my KB, which we just did, okay? I know the equation. Those are some things that I need to make sure I've got. And then I've got to calculate molality. To do that, I've got to change that to kilograms, which he just said. And I take moles divided by kilograms, and I get 4. So 1 divided by 0.25 is 4. Okay? Then I'm going to plug it into this equation. Now, wait a minute. What did we decide glycol? What was the I on glycol? 1. If they do not give me a formula, or if I don't know what it is, 1. Sugar, C6H12O6, 1. Okay, I don't break it up into how many carbons, how many hydrogens, how many oxygens. It doesn't do that. Okay, it just stays as one thing. Plug everything in I know, and I end up with a change in temperature of the boiling point. What did I just tell you on the last graph? Stay with me. What did I tell you on the last graph? What do you do boiling point? It goes up. So what's the normal boiling point of water? 100 degrees Celsius. So what am I going to do? I'm going to add it to 100, and I get the new boiling point. Okay? Make sense? Doing okay? All right. 0.52 is the KB for water. On that one, it's 0.51. It actually has 0.518. That's fine. It doesn't matter. You're not going to be that far off. Okay, so going forward, freezing point depression, we're going to do the same kind of thing. We're going to get the KF from the graph. We're going to use this 0.29 molal NaCl. So I just plug in everything I got. Wait a minute, NaCl. I got to deal with the I. What's the I on NaCl? 2. Great. I see fingers up for 2. Now, plug everything in, times it through, and I get 1.1. Okay, what do I do with that? Freezing point depression. It's lower, so what's the freezing point of water? 0. So if it's lower than 0, I'm going to subtract it. So it ends up being negative. That's why I had you put a negative on that side of the chart. So you know that freezing point depression's got to be lower, and it's probably going to be negative because we're going to be working with water a lot. All right, so let's do another one. Here we have a 5.4 molal solution of NaCl. Is that stronger or weaker than what I had before? Is it more saturated or less saturated? It's more saturated. So is the freezing point going to be higher or even lower? It'll be even lower. Okay. It's a guessing game. It's one of the others. Okay, so I do the same thing, plug it through, and I actually get a freezing point depression of 5.6. Subtract it from 0, and I get negative 5.6, right? Okay, so that's the end of what I'm going to talk to you about today. What did we not get filled in? How to find I was if it's ionic, how many particles it goes into, how many ions it goes into. Okay, what else did we not get? Yes? Freezing point depression? Oh, it should say depression. Fix that. Freezing point depression. Freezing point depression is the same equation. The delta T equals KMI. Okay, it's the same one, except it's going to be KF, or KF freezing point. Okay, anything else we missed in your notes? Did we get everything else in your notes? Awesome. Okay, so let's go to the lab. We're going to do pre-lab today, and we'll actually do lab next time. And if you're really good and get the lab done, we're going to do application of the lab. If you look at the back page, you can see the application. What's the application of this lab? Making ice cream. So we want to get the pre-lab done, know what we're going to do in lab, be able to get lab done, and come back and do the application, right? And then we'll do the review Kahoot while we're doing application. So let's go through this lab real quick. So here's our equation that we've just been learning. Delta T equals KMI, right? Here we're going to use KF because we're worried about freezing point. Each lab group is going to get their own chemical that they're going to be doing, and then we're going to share it as a group. So we're going to get lots of information from only being able to do one thing. Does that make sense? Okay, so let's read this through. Let's just go, Sarah, let's start with you and work our way up. Everybody just read a paragraph, or read a sentence. I'm going to pass this on.
Just the first sentence.
First sentence, I'm going to pass it on.
When a solute is dissolved in a solvent, the freezing temperature is lowered in proportion to the number of moles of solute added.
This property, known as freezing point depression, is a colligative property. That is, it depends on the ratio of solute and solvent particles, not on the nature of this substance itself.
The equation that shows this relationship is where T is the freezing point depression, Kf is the freezing point depression constant for a particular solvent, and M is the molality of the solution, and I is the number of ions that an ionic compound will split into.
In this experiment, you will find first the freezing temperature of the pure solvent, water H2O.
You will then add known mass of different solutes to a known mass of ice and determine the lowering of the freezing temperature of the solution.
By measuring the freezing point depression, delta T, and the mass of the solute, you can use the formula above to find the molality in moles per kilogram.
You just left out. Okay, so what we'll do is we're going to be doing the pre-lab today, but I want to go and scroll down a little bit to the next page so we can sort of see what's going on. So in the procedure next time, what we're going to do is we're going to wear goggles, of course. You're going to have a thermometer. We're a small enough class that we probably are going to get each of our own thermometers for our group. You're going to obtain a styrofoam cup. And I just love how it disappears after I drew it. That is just awesome. Okay, let's try it here. Here's a styrofoam cup. You're going to weigh it. You're going to put it on a scale, and you're going to weigh it. Then you're going to put in about 200 grams of ice while it's on the scale. You're going to write down what that is. And you got a thing down here to do it. Then you're going to add about 100, well, it should be 200 grams of water, yeah. So this is messed up. This should be water, and this is ice. So it happens, okay? So you're going to add about 200 grams of water and then about 100 grams of ice. Then you're going to get the temperature, whatever it is. Okay? And then you're going to weigh out in a small beaker, because there's going to be a little small beaker, 2 grams of whatever salt I give you. Okay? Then you're going to put that 2 grams into here, and with your temperature probe, you're still stirring that, and you're waiting for the lowest temperature it will come to. The lowest temperature it will come to. And you record it. So you've got the lowest temperature of just the ice and water right here, and the lowest temperature of the ice and water in the solid. That's what you need to get done during lab. Okay? Then when you come out of lab, I'm going to erase this, so I don't want it to accidentally save for me on there. Come on, big eraser. Okay, I'll come back and do that in a minute, because it doesn't want to do that right now. Okay, when you come back to the classroom, you're going to be filling this in. I'll give you a team number. Actually, your team number is the number on your desk, okay, the yellow one. And you're going to put up this stuff for your chemical. You're going to tell me what chemical you used, what was your solution freezing point. Up here, you're going to put what your ice water freezing point was, the lowest temperature of the ice and the water by themselves. You're going to figure out the molality of the solution. And you're going to have research what hazards this chemical has, because it might have a great freezing point, but it might be hazardous as heck, and I don't want to be around it. And you're going to also research the cost. Okay? Now, you can do that with your phones or grab a laptop or whatever. Then we've got some analysis questions that you're going to answer after. Now, once you get this stuff up in the grid, then you can start making your ice cream. Come sit down and we'll do a review Kahoot next time. Okay, so we want to do this fast so we can make our ice cream and then we can have some fun as a review. So let's go back up to what needs to get done today. So we have a pre-lab that goes all the way to 11 on the pre-lab. Okay. All right. And you know what? The more I think about it, I think I did this messed up. I think this one should have been ice, because you're going to want more ice than you're going to want water. $200 grams of ice and 100 grams of water, because you just want enough water to, because otherwise the ice isn't going to last. So let's change that the other way. Let's leave out ice and water. Okay, sorry. So you had 200 grams of the ice and only 100 grams of the water. That's what happens when you're thinking, when you're standing up in front of the group, when you have a mistake on your thing. Okay, so I'm going to give you, your group, one of these. Now, you're going to give it back to me. There are some that have hepta or pentahydrate. What that means is as you go and write your formula, you're going to go dot. If it says hepta, it would be 7 waters. If it says penta, it would be 5 waters. This does not mean times, it means attached. So when you go and do your formula weight for that, you add up the formula weight of whatever this is, you add it to 7 waters weight. So I go 7 times 18.015, and I would add it to this. Does that make sense? Okay. Oh, now it erases nice for me, really? Okay, so I'm going to pull out. I'm going to give you your thing. If your partner's not here, just pretend like they are. If you need help from the group next to you, you can. Okay, so you've got your assignment now. So you're going to write down the name of the compound right here on number 1. You're going to do the chemical formula. You're going to decide the I. Now remember, if it is it has a polyatomic on it, it probably is ionic, and how many parts will go in. Or if it's far apart on the periodic table, it's probably ionic. How many parts will it go into? If it's close together, the I is going to be what? If it's close together on the periodic table, what's the I? 1. I is 1. Okay? So after you get your 11 questions done, you've also got a worksheet that says colligative properties. This one is all about delta T equals KMI. Would you write that at the top? Delta T equals K, the italicized M, and it's actually an italicized I. So that's the equation you're going to be using on that colligative properties worksheet. Okay? All right. We're going to work together. I might even forego the end quiz today just because, so you give you a little bit more time to work. Okay?